So that's me. I am a fairly recent graduate from the University of Nebraska, and I am also a postdoctoral scholar with the G. Magnotta Research Lab under Dr. Mulaney Wills, who is here today. Another little piece of background on me, just to kind of contextualize a little bit about what you'll be hearing today, is I am a Minnesota native. Minnesota is a Lyme endemic state, so that means that we fully agree that Lyme is in Minnesota. People get it all the time. That's our state flag. We adopted it just a couple of years ago. It's new to us. It caused a lot of drama in the state. It was good times. And my interest in Lyme disease and kind of vector-borne disease in general comes from being in this Lyme endemic state. Lots of ticks, lots of Lyme. I myself has been diagnosed with Lyme when I was very, very young. Had family members, friends, my spouse, dogs, diagnosed with Lyme and various other tick-borne diseases throughout the years. So pretty early on, I was aware of tick ecology and the outdoors, and this kind of led me down this road to pursue infectious diseases epidemiology, and eventually led me here today. So a little bit of background, a little outline of what we're talking about today is we're talking about Lyme disease. So I'm going to present to you some research that I did during my PhD program that focused on surveillance of ticks that transmit Lyme disease, as well as how environmental factors influence tick abundance and ultimately disease rates. We're going to start with a little background on Lyme disease and how it kind of fits into the One Health framework for those of you who might not be familiar. And then since the research I conducted was out of Minnesota, even though I did my PhD in Nebraska, all of the data came from Minnesota. We're going to get a little bit more specific about Lyme in Minnesota and ticks in Minnesota. We're going to transition into two kind of research projects that I did during my PhD, and that was comparing active and passive surveillance systems within Minnesota and how they relate to disease. And then we also looked into environmental factors that predict tick-borne disease or tick-borne abundance and disease, both in the same year and with time-lag effects. And then just like a little bit about current and ongoing work. Got it, nailed it. So first, like I said, we're going to talk a little bit about the background. So as an epidemiologist, I have to have an epidemiology of Lyme disease slide, right? So the agent that causes Lyme disease is Borrelia burgdorferi, and in some parts of North America, also Mayonii. The host is most commonly the white-footed mouse, but there are over 60 species of competent hosts for Borrelia bacteria. We pick on the white-footed mouse a lot because it's very prevalent, and it's a really good host in that it's great at transmitting infection back to the ticks above many other mammals. So very prevalent, and it's really good at transmitting infection. The vector is what is shown here, the Ixodes scapularis tick. You'll also have heard this referred to as the black-legged or the deer tick. I have pictured here the adult female and male, the nymph life stage, followed by the larval life stage. You can see the size difference and kind of appreciate the size of the tick in general. A lot of people are familiar with dermacenter species ticks, the dog tick. These are a little bit smaller than them even, so they're quite small. And interestingly, these vectors also transmit the pathogens that cause anaplasmosis, babesiosis, and ehrlichiosis, which are all present in Minnesota. And I believe they're also all present here in Ontario as well. Not going to belabor this too much, but as we are in a One Health seminar, we should probably talk a little bit about how ticks interact with the environment before we dive in. And so this is the deer tick life cycle. It lasts about 2 years total. We start the life cycle in the center of the graphic here in the springtime. In the early summer, they come out as larvae, and at this stage, they are not infected. So even if the mom tick was infected with Borrelia, the ticks that hatch out and become larvae will start their lives uninfected. This is, however, the life stage that they are most likely to become infected with Borrelia, and that is because they're going for those small blood meals or small mammals for the blood meals, and that is very commonly including that white-footed mouse that we talked about before. So provided they find a blood meal, they will transition into their next life stage, nymph, where they'll emerge in the springtime. At this stage, they're going to be going for slightly larger mammals for blood meals, and that will often include humans. So this is when the life stage that we are at the highest risk for human infection. And it's mainly because of the size of those ticks, because they're so small. We are not as likely to find these ticks on our person, and so they're likely to stay on for a good amount of time and transmit infection, as opposed to the adult ticks that you're a little bit more likely to find on you in time to remove them from the infection. So what does Lyme do to humans? What does it do to the body? So these are just not an exhaustive list of symptoms, but I just kind of wanted to point out there's 3 stages of Lyme disease clinically. We have early localized, early disseminated, and late disseminated stages. Early localized stage, outside of that erythema migrans rash, which is pictured here, the symptoms are pretty vague. We have fever, fatigue, very vague symptoms are in that early localized stage. And really only about 70 to 80%, depending on the study. Those figures change depending on the study. Sometimes they can be a little bit lower than that even. You might not even get the rash. This is kind of the classical presentation of a bullseye. It doesn't always look like that. Maybe it's in a part of your body where you don't see it, like in your hairline. Many people miss this rash, misdiagnose this rash, and that often leads to misdiagnosis of Lyme disease itself. If it's not caught early and treated, it will progress. The symptoms throughout early disseminated and late disseminated will progress, getting worse and worse, and becoming a little bit less vague over time. Treatment is generally, as long as, like I said, it's diagnosed fairly early, going to be oral antibiotics, a relatively simple course. The more the disease has been allowed to progress, however, sometimes it is intravenous antibiotics are needed. Often that is coupled with an inpatient hospital stay. And no matter what stage of infection it is diagnosed and treated in, there is a chance of chronic complications and symptoms to continue beyond treatment. And as the disease is allowed to progress, the longer it is between diagnosis and treatment, infection and treatment, we have a much higher risk of that chronic complication popping up. So this is a lot more symptoms that you might see in Lyme disease. And it's a little bit overlapping with the last slide, but I think that this is a great image just to show how systemic this disease really is. It really doesn't affect just 1 or 2 body systems, it affects the whole body. And this really speaks to that. Also, all of the symptoms listed here, there's a ton of them, are relatively common, but it would be uncommon for somebody to experience all of these symptoms. And so that really goes to show, I think, how 2 people with the disease can have totally different presentations, and that really complicates diagnosis and identification of the disease. So I always think that's important to kind of point out. So hopefully at this point we're seeing how it fits into the One Health framework. We have environmental health, land use, deforestation, climate change, and weather patterns. We're going to be talking a lot about weather patterns specifically and how that interacts with tick density in an area. But all of these things are affecting both the animals and the ticks, how they survive, how they thrive or don't thrive from one year to another. Animal health, wild animal biodiversity, those white-footed mice are important to the tick life cycle. We have evidence that shows that as biodiversity in an area increases, ticks have access to lots more different types of mammals, and that will often decrease the rates of Lyme in the ticks, or Borrelia in the ticks. So all of these animal health things are important to Lyme in general. And then, of course, the human health aspect, where we have acute Lyme, chronic Lyme, and pre-existing conditions that may be affecting how people react and how severe of disease they get from that Lyme. So of course, I'm in Canada now, so let's talk a little bit about Lyme disease in Canada. So these are, as of 2024, the number of Lyme disease cases reported by province. We can see on the 2 graphs on the right, both the number of cases and the incidence per 100,000 population is increasing over time. We see dips and spikes from one year to another. Largely that's going to be because of weather changes from one year to the next. Some years we have really conducive environment and weather to tick populations. Some years not so much. That's often reflected in disease rates that we see in human populations, but overall, a very steady upward climb over time. We do see that in the map, while there's a couple of cases along the west side of the country, largely it's focused along the east side with Ontario and Quebec taking the brunt of things. And so we kind of have this dichotomy of Lyme disease within the country, but really mainly on that east side. And in the US, we see that reflected as well, right? Is traditionally, we see kind of a smattering of cases in California is usually where we think about seeing Lyme disease, and up into the Pacific Northwest. But largely, Lyme is very much centered in the upper Northeast and the Midwest, specifically Minnesota and Wisconsin. I do have Minnesota outlined in red. Like I said, I'll be talking about Minnesota, and so for those of you who might not know which state that is, it's that one. And so we also see over time, 1995 to 2023, huge increase in Lyme in that span of time. It's also important to note that the CDC estimates that actual cases are expected to be about 10 times higher than reported, and we expect that to also be true for Canada. And so the numbers that we see are really just the tip of the iceberg in both situations. So this map reflects tick-borne disease risk, including anaplasmosis, babesiosis, and Lyme disease. Lyme is the most common by far in Minnesota, so that is mainly what's driving the tick-borne disease risk in this map. We see a really clear pattern across the state with the highest risk on the northeast side of the state and the lowest in the southwest. The data that I talk about is from the 7-county metropolitan region that is outlined in blue on this map. And that is the most highly populated area of Minnesota. Most of our population resides within those 7 counties. That's where our capital is. It's where Minneapolis is. You guys, probably all of America is there. Lots of fun things. Let's see here. And again, even within that little area, we see that risk trend repeated, right? We have both high risk and moderate risk within that 7-county region, which makes it a really interesting thing. I always think this map on the right is a really interesting map to look at when we talk about Lyme disease and the vector Ixodes scapularis in Minnesota, as well as in the country in general. So Minnesota specifically is home to 4 unique microbiomes, and that includes aspen parkland, coniferous forest deciduous, and prairie grassland. You can see that there's like pretty clear definition from the biome type to the risk that we see in the state, with coniferous forests being where ticks really thrive very well and where the disease kind of runs rampant, and then that moderate area being the deciduous forest, and they don't seem to thrive as well in the prairie grassland. We also see, if we're looking at that map of North America, that coniferous forest range increasing into the area that coincides with where we are seeing Lyme disease in Canada in that other risk map that we showed. And then again, that coniferous forest range in the upper northeast of the US as well. So I just think that that's fascinating to look at and think about. So given the high risk of Lyme in Minnesota, and the dips and spikes from one year to the next, how do we track and assess the risk? So vector surveillance is kind of the easy answer to that. It can help us to better understand tick abundance, which is shown to be associated with disease risk. If the vector is present, it's possible that the disease is present as well. It's also a really good way to monitor introduction of tick species to geographic areas and expansion of those vectors. It's often coupled with testing of the ticks or testing of the hosts that the ticks are found on. So the group that I worked with did small mammal trapping, and then they would test occasionally the host's blood for disease. So there's 2 main types of vector surveillance that we're going to talk about, and that's active and passive. Active surveillance for ticks is systematic, field collection. It includes flag sampling, small mammal trapping, like I said, CO2 trapping. Passive surveillance is voluntary submission of ticks, often for research or government purposes. One common way for passive surveillance is I've seen groups ask veterinarians to submit ticks that they find on animals that are brought into them. So that's a kind of cool way for passive surveillance. And then I'll talk a little bit about another form of passive surveillance that we used in our studies here. Active surveillance is very timely, and it's good at monitoring trends over time, but it can also be very time-consuming and expensive. On the other hand, passive surveillance is less expensive because we're just asking people to participate. It's great at uncovering new geographic trends where we might not think to look with active surveillance. And it can reflect where people are encountering ticks rather than just where ticks exist. And that can inform prevention and active surveillance efforts as well. While all forms of surveillance are subject to some level of bias, passive surveillance is subject to bias a little bit more than active surveillance tends to be. So now we're going to dive into our research efforts in comparing the two vector surveillance methods. So I ended up using 3 data sets. I have 2 listed here. So for tick surveillance, we had active surveillance from the Metropolitan Mosquito Control District. I'll refer to them as MMCD. They performed surveillance through removing ticks from small mammals that they trap, and they've been conducting tick surveillance since 1990 across 100 sites in the 7-county metropolitan region. So that's a very vast, deep data set. They gave us line lists that included the location and type of the small mammal that they trapped, the number of ticks found on that animal broken down by both species and life stage. For our passive data set, we used iNaturalist, which some of you may have heard of before or used in the past even. It is a crowdsourced species identification and recording system is what they call it. People anywhere can download the app on their phone or go to the website and record observations, including photos, geocoded locations, date of observation, and more. Data from iNaturalist is freely available, and it is active in Canada. I've seen signs of people encouraging use of it, and so if you have a similar project, iNaturalist is a really great thing. So I downloaded observations from the 7-county region to match the MMCD data set timeline and space. And I don't have it shown on this slide, but I also used Minnesota Department of Health data. They provided me with number of human cases of Lyme disease by county in the same time period. So to compare the 2 data sets, the 2 surveillance methods, we used descriptive statistics to compare the output between the 2, and then to determine whether there was an association between tick abundance in the data set and cases of Lyme. We used generalized estimating equations with negative binomial distribution. We gave the kind of heads up that I have a master's in biostats, so some of this will get a little bit in the biostats realm, but I'll hope to try and make it make sense a little bit. The outcome that I used for that model was the number of cases of Lyme disease, and we used 6 variables for tick abundance, including the total number of ticks, broken down by species, so both Ixodes and Dermacentor were our 2 main species of ticks, and then 3 life stages of ticks as well. We adjusted all of the models for county as a repeated measure, and we ran the analysis on the 2 tick data sets separately, and then we did it combined as well. Okay, so when we explore the 2 data sets, I have just over 9,000 observations between 2018 and 2023. You can see the number of observations by year and tick species in the graph with MMCD observations on the left, iNaturalist on the right. We had extra years from MMCD, so I have that outlined in gray. Those weren't included in the analysis, but since I had them, I just kind of wanted to show what that looked like. There is a difference in the y-axes, just kind of note that. This reflects a really big difference in observations, the number of observations between the two data sets. MMCD accounted for 97% of the observations total that we had. So increased popularity of the iNaturalist data set, of the iNaturalist app, is evident in the steep uptick that we see over time. They do actually have data going back beyond, or back to 2014, but there was so few data points at that time that we restricted to 2018 forward. Okay, so here is kind of the geographic distribution of what we saw when we compared the two data sets. When we compare it, we can see the heat map here. I have MMCD on the left. Again, that is the active surveillance, and then passive is the iNaturalist on the right. Darker blue reflects more tick observations. Both maps tend to mimic that tick-borne disease risk map that we saw in the background, with the most ticks being in the northeast side of the 7-county region and the least amount of ticks being in the southwest. Again, that reflects that risk map that we saw. Both maps are in general agreement with each other. There's a little bit of difference, but it's pretty accurate in general. It's worth noting in the iNaturalist map that Hennepin County has the largest population by far. Hennepin County is where Minneapolis is. They have 1.3 million people in Hennepin County. And sometimes we would expect passive crowd surveillance systems to reflect population rather than actual abundance. But given that the county with the largest population is only the 4th biggest contributor, and the distribution between the data sets are in general agreement, it seems that iNaturalist is actually reflecting encounters and not necessarily the population size of that county. Supporting this, we have Washington, Anoka, and Dakota counties. In dark blue are the largest contributor for tick observations in iNaturalist. They also have the highest incidences of Lyme disease in the metro. Like I said, we have our highest risk disease area, also reflecting our highest tick areas as well. So this is a breakdown by species between the two data sets. The outside ring in the figure is, iNaturalist. And that had a majority of dermacenter variabilis ticks, variabilis ticks, and the inside ring is the MMCD data set. That has a majority of Ixodes scapularis. This is really reflective of the type of surveillance that was done. MMCD was literally created as the Ixodes scapularis ticks started moving into the Twin Cities metro in the late 80s, early 90s. They wanted to track how that tick was expanding throughout that geographic region. And so they have chosen small mammal trapping, and specifically in surveillance areas where they expect that tick to be found. So they've done a really great job at finding this tick. Whereas iNaturalist, human encounters, I would say that in the Twin Cities metro, the dermacenter tick are more prevalent than the Ixodes scapularis, and that's what the majority of people are coming into contact with. And so this is life stage between the two data sets. We see, again, iNaturalist on the outside with predominantly adult life stage ticks. MMCD had predominantly larvae, that's in the center. Again, very reflective of the type of surveillance that it was doing. MMCD was trapping small mammals, so we will tend to see early life stage ticks reflected in that. iNaturalist is people finding ticks on themselves and their dogs and companion animals in general. And so we would expect people to be much better at finding larger ticks. And to kind of support the idea that sometimes it's very difficult to find ticks, this is my favorite image. I try to include it in every Lyme presentation that I do because it grosses people out and I love it. So this is from CDC, posted this. They said, ticks can be the size of a poppy seed. Can you spot all 5 ticks in this photo? And it's a really great way to show that ticks are gross. No, I'm just kidding. They're great. Ticks are great, but they're also very small and hard to find. For those of you playing along, these are the 5 ticks on the poppy seed muffin. So this is the results of our analysis exploring tick abundance. on association with disease. So the outcome in this case, like I said, is the number of Lyme disease cases. And we used the 6 different predictors for tick abundance across the combined data set in that top chunk, the MMCD in the middle, iNaturalist in the lower. Don't try to stare at that table too long, it's a lot of information. Overall, we can see that between 3 data sets, no matter what tick species we're looking at, what life stage we're looking at, there is a positive correlation to human cases of Lyme disease. So no matter which data set we're looking at, as the number of ticks increase, so does the expected number of Lyme disease cases. In all of the models, the effects are significant. You'll also notice that the effects are relatively small. This is the estimate for the difference in 1 tick observation. And so we would expect the estimates to be very small. So to kind of make it a little bit more interpretable, we turned it into a graph. This graph is showing the predicted number of cases of Lyme disease from the number of Ixodes scapularis ticks in both of the data sets. And we see, indeed, as the number of ticks increase, so does the expected number of cases of Lyme disease. So final thoughts on active versus passive surveillance. So geographic exploration shows that iNaturalist reflected where people are coming into contact with ticks, not necessarily just reflecting population estimates. This complements the active surveillance by identifying where exposures are actually occurring and can help us to inform public health efforts and education efforts to prevent Lyme disease in the areas. We also saw iNaturalist observations of any tick species, including Dermacentor variabilis, which I want to be clear does not transmit the pathogen that causes Lyme disease, but it was still associated with Lyme disease counts. And so this suggests that passive surveillance, observations of ticks of any kind, are reflecting the risk of tick-borne disease, probably through just being in an environment that is conducive to ticks in general. So the analyses also showed that tick abundance from active surveillance of early life stage ticks in any life stage is associated with Lyme disease cases in the same year. And we can obviously use that to predict when we're going to have a high Lyme year. If we start seeing a season with lots and lots of ticks, we can expect to see a lot of Lyme disease in that season. So now we're going to take it a little bit of a step further. We know that tick abundance is predicting human cases of Lyme disease, but how can we better predict when that tick abundance season is going to hit? And this is where environmental predictors come in and where those highs and lows of tick abundance from one year to another and Lyme abundance from one year to another comes in, is because several studies have shown that the physical environment and weather are associated with tick abundance. A lot of that research is based in the northeast part of the US. There's not a lot in the Midwest. There's not a lot in Canada. I was able to find some studies showing that landscape factors had similar effects. So if deciduous forest is having the same effect no matter where you are. However, climatic differences like precipitation and temperature can often have varying effects depending on what part of the country, what region of the area that they're in. So this leads to the question, can we use environmental factors to predict tick abundance measures? And then can we take that a step further and can we use environmental factors to predict Lyme disease risk? Now, to address this, we used active tick surveillance data. So we used the MMCD data with the small mammal trapping. And because they do small mammal trapping in a very systemic way, looking at the same 100 survey sites every year, the same number of times, we were actually able to use that data set for estimates of small mammal abundance, as well as to calculate the ratio of the white-footed mouse to other mammals that they were trapping to get kind of a rate of that biodiversity, host diversity in the area. And so like I had said in the background section, I think, host diversity has been shown to decrease Lyme, and so this was just kind of a fun way to test that theory. We used Minnesota Department of Health data for reported cases of Lyme disease. And then we used 2 data sets for environmental and weather data. Most of the weather data came from a website called TerraClimate, which is a database that is open access, and you can get weather and climate data by county all across the US. And so we use that to get high and low temperatures for each day, which we use to calculate the number of degree days in the spring. We also used it to calculate the number of days in the winter that the temperature dropped below 0 degrees Fahrenheit. We got the values for snow water equivalent, soil moisture, vapor pressure deficit, and the Palmer Drought Severity Index. We also used openly available data from the Minnesota Department of Natural Resources for snow depth, all aggregated by county. And we used logistic regression to model the odds of a high tick abundance or a high Lyme disease season or year, incorporating county as a repeated measure. We used 2 different methods for variable inclusion in the model. This kind of was a nod to my biostat side of testing 2 different methods of variable selection for a model. So we used backward selection, which is very traditional, and in that, all variables are entered into the model and then systemically removed until all the remaining variables have a p-value less than 0.05. And then the other method that I used was gradient boosting, which is a machine learning model method. And that produced variable importance and relative influence on the outcome measures. And then we included those that were most important and influential into the logistic model, logistic regression model. So given that the lifespan of the Ixodes scapularis tick is about 2 years, we wanted to assess whether time lag effects were in the data. So to do this, we used the same methods that I just described, and we incorporated 1 and 2 year time lags into the outcome. So this table shows the average value for each predicting variable by high and low tick abundance years. We defined that as being in the upper 50th or lower 50th percentile. The table is for all tick abundance, not restricted for species or life stage. In this unadjusted analysis, small mammal count is the only variable to be significantly associated with a high tick year, with more small mammals in high tick abundance years than low. And a couple of other variables show some degree of significance. There we go. Show some degree of difference between high and low tick abundance years. Most notably, I thought, was PDSI, that is the drought index, and also soil moisture. So we do know that ticks are very particular when it comes to moisture content. They like somewhere in between, right? They don't want too dry, they don't want too wet. And so those are, make sense as important variables. So here's the table for results. It's a lot to look at, so we're gonna try and break it down a little bit because this is the one with environmental predictors effect onto these outcomes in the same year. We're going to look at the same table with a 1 year and a 2 year time lag as well. So let's acquaint ourselves with the layout a little bit. So I have the 4 outcomes that we have modeled along the left-hand side as all ticks, and then broken down by species, Ixodes scapularis and dermacenter. At the very bottom, we have Lyme disease as the outcome as well. We have the predicting variables are listed along the top. You'll note that for each outcome, there's 2 rows. A gray row is the result of the backward selection built model. The white row is the result of the gradient boosted model. The model estimate is populated when the variable was included in that model. So if it was excluded using our variable selection method, there won't be an estimate there. So that's kind of the easy way to see that. On the far right is the area under the curve value. That is basically a measure of how well that model is explaining the data. So that number will range from 0 to 1, with 1 being the best, 0 being the worst. So higher numbers are better. And so kind of with that orientation, we can talk about the actual output. When we look at the top chunk of the table, across all of the outcomes, we do see soil moisture and small mammal count to be pretty consistently associated with high tick abundance years for both all ticks and Ixodes scapularis ticks specifically. The direction of association for the variables is consistent. So meaning that when it's negative the whole way down. When it's positive the whole way down. And across the models, we see area under the curve is highest, so the AUC value, when modeling for the Ixodes scapularis ticks. And across all models, the backward selection method is yielding higher model accuracy, so to speak. It's looking like a better model overall than the gradient boosting method was. When we look at the Lyme disease outcome at the very bottom, we see decently high AUC value. Oh, there we go. AUC values, again, with the backward selection model method being higher. There is not a lot of agreement in variable inclusion between the two models. If it's included in backward selection, it's not in the gradient boosted and vice versa. So weren't quite sure how to interpret that, as there wasn't a ton of agreement between the two. So this is with a 1-year time lag. We see soil moisture, small mammal count remain consistently associated with tick outcome measures. Again, those directions of associations remaining the same across models. We also now see that snow water equivalent, days below 0 degrees, degree days and mouse ratio are also consistently associated with the odds of a high tick year. In some of these cases, with degree days and mouse ratio, we do see some differences in the direction of association. This suggests that these variables are important, but there's room to explore what other factors may be affecting the changes in directionality. Again, we see area under the curve is generally higher with the backward selection method, and also in all models, area under the curve is higher with this 1-year time lag than it was in the last table with no time lag. So that's suggesting that these models are better predicting the outcomes with a 1-year time lag than it was in the same year. And when we look at the bottom chunk of the table, we see that the only predictor for the gradient boosted model 1 year out is that drought severity index. Despite only having one predictor, the AUC is 0.85, which is pretty good. And we don't actually have any information for the backward selection model. That one actually kicked all of the variables out. So traditional methods in this particular situation failed us, and we only have the gradient boosted. Okay, so this is for the 2-year time lag. Palmer drought severity index remains associated with high tick year along with soil moisture and snow depth. They're all consistent in directionality. AUC values for those tick models remain high. And some outperform the models with the 1-year time year lag, but some of the AUC values are higher with the 1-year lag versus the 2-year lag. So this suggests that some of these variables are probably more predictive 1 year out, and some of them are a little bit more predictive 2 years out. So by combining that information, we can make a supermodel. For Lyme disease, again, we only have the gradient boosted model as the backward selection systemically removed all of the other variables. Looking at that gradient boosted model, we see a really high AUC value with several variables predicting high Lyme disease year. PDSI is the only variable that predicted a high Lyme disease year without a lag, with a 1-year lag, and with a 2-year lag. And the AUC value increased from 1 year to another, and the strength of the estimate also increased from no time lag to 1 year lag to 2-year lag. Everything increased, which suggests that the drought severity index is most predictive 2 years out, but it's predictive same year, 1 year out, just becomes stronger. So final takeaways from that analysis is based on the AUC values, we found that environmental variables most accurately predict tick abundance 1 year in advance and Lyme disease 2 years in advance, with that drought severity index being the most commonly associated with high Lyme years. The machine learning built models were successful in analyzing the time lag influences when our traditional backward selection failed with those Lyme disease models. So integrating the approach with both the backward selection and gradient boosting can help to fill some gaps when we previously may have failed to be able to predict. So the model output from this objective suggests that we can predict high Lyme years in advance. In AIM-1, we show that tick surveillance in the same year can also help to predict Lyme cases. Combining environmental prediction methods with existing surveillance offers opportunities for us to plan and better educate the public when there is high Lyme disease risk. And at the time that I was working with MMCD, and to my knowledge today, so we have this huge data set that's looking at tick surveillance, and we know that tick abundance is influential on Lyme risk. They don't do anything with that data from a public health perspective. It truly was created to monitor vector expansion throughout the region, and that's all that they've used it for. The public health department is aware that they do it, but they don't really collaborate on anything. And it does kind of make one wonder, how often does this happen? And I think we've all seen examples of this where there are these great data sets available that you can do such amazing things with, and we're just not utilizing them properly. So I think that this also kind of speaks to that, that we're able to predict Lyme disease risk, and we can use that for very important things, but it's just kind of sitting there. So what's next, and how does this connect to work that why am I here at the university? So there's a lot of really cool research being done out of the Magnotta lab, but one of those efforts involved dragging for ticks in the Rouge National Urban Park in Toronto. I think that that's a super interesting area to look at for the same reason that the 7-county metropolitan is it's looking at this intersection between where we know tick populations exist, but we also know that human populations exist and interact with the environment. And so I think that that's really important, because just because you have ticks in an area, if you don't have humans encountering them, it's not going to have as much of an impact. So what they've found in the past 2 years are large populations of ticks with very high rates of Borrelia within those tick populations. The original purpose of those draggings were to create a biobank of Borrelia. And so the surveillance area was fairly limited to a small portion of the park. However, because of that surveillance, they have noticed that ticks collected from meadows have a higher rate of infectivity of Borrelia than the forested areas do. And so this year we're expanding to other areas of the park to explore whether that's unique to that particular area or if it's consistent with other areas of the park. So I think this connects in quite a bit with the work that I've done in the past with environmental things, getting more into that landscape piece of the puzzle with ticks. And so we do look forward to our first tick drag of the season within the next month or so here. Looking forward to that. And now, as I've just told you, there's tons of ticks and tons of disease. Don't be afraid. Please go to parks and spend time outdoors. Use that more as a reason to be aware that you are in a tick-conducive environment, and to take appropriate precautions like wearing long sleeves, long pants, doing tick checks, all of the things, staying in the center of paths rather than walking through the tall grasses. But yes, I would hate for people to hear that there are lots of ticks and disease and stop going outdoors, because it's good for your health, physical and mental. And yeah, with that, I would love to hear any questions that anybody has. And thank you all for listening.